All right, let's take a look at the practice test. For the instructions, we're asked to find the exact value. All right, let's take a look at the first problem. So here we have the inverse sine of negative square root of 3 over 2. Before we answer this, I want to revisit the graph of y equals the inverse sine of x. So what's the domain? Looking at the graph, we can see that it's from -1 to +1. Let me just write this out. So this is the domain. It's going to be from -1 to +1. -1 and +1 are included. Now for the range, which is really what we're going to focus on here, you see it's from -pi/2 to pi/2. Both are included. So from -pi/2 to pi/2. Okay, so now that we've established that, let's go back up, and I'm just going to copy this. So we have the inverse sine of, and we have negative square root of 3 over 2 as the argument. What you want to do is you want to think about that range. So in other words, the result of this guy right here is going to be from -pi/2 to pi/2. So if this guy is positive for the argument, you want to work in this first quadrant here. If this guy is negative, you want to work in this fourth quadrant here, but you're going to be rotating clockwise. So in other words, if I think about where the sine value is negative square root of 3 over 2, well, looking at my unit circle, you're going to see that right here. That's at 4pi/3. And then you're going to get that again right here at 5pi/3. So we're not interested in this guy right here because it's in quadrant 3. So I'm just going to delete this, and I'm going to focus on this one right here. So this right here is what we want to think about. But again, we can't use 5pi/3 because that is not within the range of the inverse sine function. So what you can do, the slow way is to say you have 5pi/3, and you're going to subtract away 2pi. So minus 2pi, so that's 6pi/3. So that gives you -pi/3. So that would be the answer there. And what you're basically doing is you're saying, okay, if I started here and I rotate, so if I rotate to this 5pi/3, well, to correct for the fact that with the inverse sine function, you're rotating clockwise, I really want this guy right here. That's the angle I want, which is -pi/3. So what you would have to do is start from here and rotate by -2pi, so by -2pi, and then come back to right there. So essentially you have the 5pi/3 minus 2pi or minus 6pi/3, which gives you that -pi/3. Now, that's the slow way to do it. What's the fast way to do this? You just realize that this guy right here has a reference angle of pi/3. So basically, if I want a clockwise rotation, this angle right here is going to be -pi/3, right? So this would be -pi/3. It's just that simple. So the answer here, let me just erase this and I'll just put is equal to -pi/3. So that's going to be for the inverse sine of negative square root of 3 over 2. All right, for problem 2, we have the inverse tangent of 0. Now, most of you know this is pretty easy. It's just going to be 0. But let's look at the graph for y is equal to the inverse tangent of x. And we're just going to think about it for a moment in case it comes up again. So basically, we know that the domain from the lesson is the set of real numbers. So in other words, it's from -infinity to +infinity. So I can plug in any real number that I want for x and there's no problem. Now for the range, this is again where you have to be careful. So it's going to be from -pi/2 to pi/2, but -pi/2 and pi/2 are excluded. When we looked at the inverse sine function, they were included, but here they're excluded. And that's because the tangent of -pi/2 is undefined, as well as the tangent of pi/2. They're both undefined because at -pi/2 or pi/2, the cosine value is 0, so you get division by 0, which is undefined. So for the range, we get from -pi/2 to pi/2, and those are excluded. Now, if we come to the unit circle, again, just like with the inverse sine function, if we have something that's positive, we're working here in this first quadrant. If you have something that's negative, you're working in this quadrant. Again, you're rotating clockwise for the negative argument. Now, in this case, you have 0. So I'm thinking about a tangent value of 0, and of course, that's not on the unit circle. We all know that it's going to end up right here with this angle of 0, but let's just think about this for a moment. The tangent of 0 is equal to the sine of 0 over the cosine of 0. And the sine of 0 is 0, and the cosine of 0 is 1. So the tangent of 0 is equal to 0. So in other words, when I go the inverse tangent, so the inverse tangent of 0, that's going to get me back to 0, which is this angle right here. All right, let's take a look at problem 3. So here we have the inverse secant of -2. So we're going to end up converting this over into an inverse cosine function problem. But before we do that, let's just look at the graph again for the inverse secant function. So y is equal to the inverse secant of x. So the graph looks something like this. And essentially, what you'll see is that for the domain, what we have here is x can be -1 or anything less. So the way you would write that is coming from -infinity, going up to and including -1. So you have a parenthesis with -infinity, and then a bracket with -1 to show it's included. And then you have the union with from 1 out to positive infinity. So 1 is included, so again, we're going to use a bracket there, and this goes out to positive infinity. So the problem was the inverse secant of -2. So is that within the domain? Yes. If you come over here to an x value of -2, well, if I go up, I'm going to have a point right there, and this is going to end up being -2, 2 pi over 3, and we'll find that in a moment. For right now, let's just look at the range and think about this in case we have another problem. So we have the range, and what is that going to be? Well, if I look, it seems like the y values start at 0 and go up to pi, with an exception of this value right here, which is going to be pi over 2. So this line in orange, this dashed line, this is a horizontal asymptote. And so basically that's the line y equals pi over 2. So the range, if you want to write it in interval notation, you could say from 0 and including 0, going up to and excluding this pi over 2. So you want to use a parenthesis here with pi over 2 and a bracket here with 0 because 0 is included and pi over 2 is excluded. And the union with, you're going to, again, exclude this pi over 2. So that's why you're using a parenthesis there. And then you're going to go up to and include. This value right here is going to be pi. And that, again, is included. So you're using a bracket. Okay, so that's the range. What we would do is actually convert this into an inverse cosine function problem. So you can say that the inverse secant of -2 is equal to the inverse cosine of, you're just going to take the reciprocal of this. So this is -1/2. You're going to end up getting 2 pi over 3. But let's think about where that's coming from with this inverse cosine function graph. So let's write that this is y equals the inverse cosine. Let me move this stuff out of the way. So of x. So here, the domain is going to be from -1 to +1. So from -1 to +1, both are included. And then your range, this is the one you really have to pay attention to. It's going to be from 0 to pi. So both of those are included. So from 0 to pi. So let's think about this problem real quick. I'm just going to grab this and come to the unit circle. So thinking about the inverse cosine of -1/2, again, I said that the range is from 0 to pi. So if this argument here is positive, you're working in quadrant 1. If it's negative, you're going to be working in quadrant 2. So this is negative. So I'm going to be working in quadrant 2, and I'm just asking where is the cosine value -1/2 in quadrant 2? So that's going to be right here at 2 pi over 3. So to answer this question, the inverse secant of -2, that's going to be equal to the inverse cosine of -1/2, which is going to be 2 pi over 3. All right, let's take a look at problem 4. So here we have the inverse cotangent of -1. All right, this problem is a little bit tricky because if you try to use the inverse tangent function in order to solve that problem, you have to make a bit of a correction. So although it may be different in your textbook, most trigonometry textbooks will show this as the inverse cotangent graph. So y equals the inverse cotangent of x. Now, the domain is the same as the domain from the inverse tangent function. So it's just all real numbers. So that's not going to change. So the domain is the set of real numbers, so from -infinity to +infinity. But the range, this is where we have to be careful. So if you look at this, you're going to have from 0 to pi, where both are excluded. So basically 0 to pi, both are excluded. And obviously, if you took the cotangent of 0, it would be undefined, and the cotangent of pi would be undefined, because in each case, the sine of 0 is 0, and the sine of pi is 0, so you'd have division by 0, which is undefined. Let's come to the unit circle and think about this. We have the inverse cotangent of -1. So based on what I just told you, you're looking in quadrants 1 and 2, and you're thinking about, well, where am I going to get a cotangent value that's -1? A lot of you know that's going to happen right here at 3 pi over 4. Because if I think about the cotangent of 3 pi over 4, well, this is the cosine of 3 pi over 4, which is negative, so negative square root of 2 over 2, divided by the sine of 3 pi over 4, which is square root of 2 over 2. So I'm going to multiply by the reciprocal, so times 2 over the square root of 2. So these would cancel, and then these would cancel. So your result here is going to be negative 1. And I know most of you know that the cotangent of 3 pi over 4 is negative 1. So that means the inverse cotangent of negative 1 is going to give me 3 pi over 4. Again, it's got to be within the range of that inverse cotangent function. Now let's talk about what you could do if you didn't have a unit circle handy, or maybe you didn't know this stuff, and you're trying to use your calculator. So your calculator probably only has an inverse tangent button. So we could say that the inverse cotangent of negative 1 is equal to the inverse tangent of, you take the reciprocal of this, so this is negative 1, but there's a problem. You need to do a little bit of a correction here because you're not going to get to 3 pi over 4. Again, with the inverse tangent function, if you have a negative argument, you're going to be in quadrant 4 rotating clockwise. So we talked about that earlier. Basically, you would be right here. Again, you would rotate clockwise by pi over 4. So right there, that would give you negative pi over 4. So how can I correct for that and get back to here? Essentially, when this happens, you're going to have to add pi to get to the correct angle. So what I would do is start at negative pi over 4, and I would add pi. So add pi, and that's going to get me right here. So I'm going to put plus this pi over here, and that's going to give me a correction. So if I key this into my calculator, essentially I'm going to get negative pi over 4, and then I've got to add pi to make that correction to get myself where I want to be in quadrant 2. So that's going to be me adding 4 pi over 4. That's just pi with a common denominator. So that gets me to that 3 pi over 4 that I'm looking for. All right, let's take a look at problem 5. So here we have the inverse cotangent of the square root of 3. So for this one, because the argument is positive, let me write this out. So the inverse cotangent of the square root of 3, you can just key this into your calculator by saying you have the inverse tangent of, you're going to take the reciprocal of this, so 1 over the square root of 3. Of course, if you want to rationalize the denominator, you can. It's not necessary with your calculator. It would just be something you want to do if you need to show your work to your teacher. So this would be square root of 3 over 3. So square root of 3 over 3. And most of you know this is going to be pi over 6, because again, the tangent of pi over 6, let me write this out for clarity, the tangent of pi over 6 is going to be the sine of pi over 6, which is 1/2, and then divided by the cosine of pi over 6, which is square root of 3 over 2. So you multiply by the reciprocal, so times 2 over the square root of 3. The 2's cancel, and you get 1 over the square root of 3, which again, if you rationalize the denominator, you get square root of 3 over 3. So the answer here is just going to be pi over 6. And again, it does not require a correction here because with the inverse cotangent function, if I have a positive argument, I'm working in quadrant 1. That's where I'm looking. And then with the inverse tangent function is the same thing. If I have a positive argument, I'm going to work in quadrant 1. That's where I'm looking. All right, let's take a look at problem 6. So here we have the inverse cosecant of a negative square root of 2. Now, if I look at my inverse cosecant function, so this is y equals the inverse cosecant of x, we think about the domain. So this is going to be, let me write out the domain here. This is going to be from negative infinity coming up to negative 1, and negative 1 is included. So from negative infinity going up to negative 1, and that's included. And then union with positive 1 is included, and then anything out to positive infinity. So that's your domain. But more importantly, we're thinking about the range. So you're going to go from negative pi over 2 to pi over 2, but you're going to exclude 0. So for the range, and this is the important one here, so for the range, we're going to say that we're coming from this right here, let me put is negative pi over 2, and this right here, let's say that's pi over 2. So for the range, you're going to say from negative pi over 2, and then you're going to go to 0. 0 will be excluded. And then the union with, you're going to cut 0 off, so it's excluded. And then basically up to pi over 2, and that's going to be included. So anything from negative pi over 2 to pi over 2, where those guys are included, we're just going to exclude 0. Now we're good to go. If I plug in negative square root of 2 in for x, I don't have a domain violation, so everything's okay. So I'm just going to come down here and write the inverse cosecant of this negative square root of 2. And I'm going to change this over and say it's the inverse sine of, again, you're just going to take the reciprocal of this, so negative 1 over the square root of 2, and I would rationalize the denominator, so times the square root of 2 over the square root of 2. So this would be negative square root of 2 over 2. So negative square root of 2 over 2. Okay, so for this one right here, if you think about where is the sine value negative square root of 2 over 2? So I'm just going to go on the unit circle where sine is negative. Again, that's in quadrants 3 and 4. So we're looking at this guy right here, so at 5 pi over 4, and then this guy right here, that's at 7 pi over 4. Now again, with the inverse sine function, if the argument is negative, I'm working in quadrant 4. So I'm going to get rid of this one right here. We don't need that. And we're looking at this right here. But again, I don't want 7 pi over 4 because I've got to rotate clockwise. Again, the shortcut here is to think about the fact that this has a pi over 4 reference angle, so this rotation here would just be negative pi over 4. Again, that's the quick way. The long way is to take the 7 pi over 4 and then subtract away 2 pi, so subtract away the 8 pi over 4, and that gives you negative pi over 4. So however you can get that straight in your mind, the other way is a little bit longer, but it's still going to get you to the right answer. So this is going to be negative pi over 4 for the answer. Okay, let's take a look at problem 7. So here we have the inverse sine of the sine of 3 pi over 4. So the inverse sine of the sine of x is equal to x only if x is greater than or equal to negative pi over 2 and less than or equal to pi over 2. Why is that the case? Let's come back up here and think about this. I'm just going to write y is equal to the inverse sine of, let's just say, x. We know when we look at this that the range is from negative pi over 2 to pi over 2, with both of those values being included. So in other words, what we're doing here is we're taking this guy right here and we're plugging it in right there, and we're saying, should I get 3 pi over 4 as the answer? That's what a lot of people do. They just try to cancel this with this and say it's 3 pi over 4. Well, no. The result of taking the inverse sine of something is going to give you something that's between negative pi over 2 and pi over 2, with those two values being included. 3 pi over 4 is not in that interval, so you cannot answer that way. So what you'd have to actually do is say that for the inverse sine of the sine of 3 pi over 4, you would first say that you want the sine of 3 pi over 4. So what is that? Well, we come to 3 pi over 4. The y-coordinate is square root of 2 over 2, so that's your sine value. So let's go ahead and say that this is the inverse sine. So the inverse sine of the square root of 2 over 2. Now, when I key this into my calculator, I'm not going to get 3 pi over 4. Because again, how the inverse sine function works, if this is positive, I'm getting something in quadrant 1. So I'm looking in quadrant 1 for a sine value of square root of 2 over 2. So that's going to be right there at pi over 4. So this would give me pi over 4 as an answer. All right, let's take a look at problem 8. So we have the inverse cosine of the cosine of 2 pi over 3. For this particular one, you can actually use the cancellation property. So the inverse cosine of the cosine of x is equal to x if x is greater than or equal to 0 and less than or equal to pi. So coming back, if we think about this, is 2 pi over 3 greater than or equal to 0 and less than or equal to pi? Well, yeah. 2 pi over 3 is greater than 0 and it's less than pi. So we can just answer right away that this is 2 pi over 3. If you went through this the long way, so you have the inverse cosine of the cosine of 2 pi over 3, and you can always do this the long way if you want. So the cosine of 2 pi over 3, that's going to be right here. So your x value is negative 1/2. So this is going to be the inverse cosine of negative 1/2. And again, with the inverse cosine function, you're working in quadrants 1 and 2. Right? So basically from 0 to pi, and if the argument is negative, you're going to be in quadrant 2 where cosine is negative. So you're looking for a cosine value of negative 1/2. So that's right here, again at 2 pi over 3. So this just reverses what you just did. So you're right back to the 2 pi over 3. All right, let's take a look at problem 9. So here we have the inverse tangent of the tangent of 11 pi over 6. So if you want to use your cancellation property, in other words, if you want to say the inverse tangent of the tangent of x is equal to x, well, that's only true if x is greater than negative pi over 2 and less than pi over 2. We have 11 pi over 6, so that is not going to be in this interval. So if I come back up here, I need to do some additional work. So I need to evaluate this first before I can take the inverse tangent. So let's go ahead and write the inverse tangent of the tangent of 11 pi over 6. Let me grab this real quick. And I'm just going to come to the unit circle. And basically, the first thing you'd want to figure out, well, what is the tangent of 11 pi over 6? A lot of you know that's negative square root of 3 over 3. But again, if you don't know that, you can still use the values here from the unit circle to get it. So you can say, what is the tangent of 11 pi over 6? Well, that's the sine of 11 pi over 6, which is negative 1/2, divided by the cosine of 11 pi over 6, which is square root of 3 over 2. So you'd multiply by the reciprocal of that, so times 2 over the square root of 3. And so these 2's would cancel, and you get negative 1 over the square root of 3. I'd multiply by the square root of 3 over the square root of 3 to rationalize the denominator. So I get negative square root of 3 over 3. I know a lot of you already know that. When you evaluate this right here, tangent of 11 pi over 6, you get negative square root of 3 over 3. So now I'm going to say that this is equal to the inverse tangent of the negative of the square root of 3 over 3. Okay, well, when I look at that, again, this tangent value, I'm working in quadrants 1 and 4. When I'm in quadrant 4, when I have a negative argument here, I want to rotate clockwise. So again, I'm thinking about this angle right here, but I'm not thinking about it as 11 pi over 6. There is a pi over 6 reference angle there, and I'm rotating clockwise. So this right here is going to be negative pi over 6. So I want to give that as the answer. So this would be equal to negative pi over 6. All right, let's take a look at problem 10. So here we have the cosecant of, we have our inverse sine of 12 over 13. So for this type of problem, I'm going to make a little substitution. I'm going to let something like, let's say u, be equal to this guy inside, so the argument for the cosecant function. So that'll be equal to the inverse sine of 12 over 13. So once I do that, I can say then the sine of u is equal to 12 over 13. Because again, if the sine of u is equal to 12 over 13, well, the inverse sine of 12 over 13 will get me to u. Now, once you've done that, you can basically say that this guy is going to be the cosecant of u. Because again, u is equal to the inverse sine of 12 over 13, so this guy right here. So the cosecant of u, by definition, is 1 over the sine of u. And here, the sine of u is 12 over 13, so just take the reciprocal, and you're going to get 13 over 12. So my answer here would just be 13 over 12. All right, let's take a look at problem 11. So we have the tangent of the inverse cosine of 3/5. All right, for this problem, just like in the last problem, I'm going to make a little substitution. So I'm going to let something like, I'm just going to use u. I typically use that. If you want to use theta, that's fine. Use whatever you want. But I'm going to let u be equal to the argument for the tangent function. So what's inside here? So basically this inverse cosine. So this inverse cosine of 3/5. So once we've done that, we can say then the cosine of u is equal to 3/5. Again, if the cosine of u is 3/5, then the inverse cosine of 3/5 is going to be u. Well, since the inverse cosine of 3/5 is u, now I just want to say that I have the tangent of u. So I'm going to put that the tangent of u is equal to what? So this is what I'm trying to find. So in order to do that, let me slide down a little bit. We'll come back up in a little while. I'm going to go back to what we did at the beginning of trigonometry. So if I have something like the cosine of u is equal to 3/5, and I know the quadrant of u, well, then I can find the tangent of u. First, let's identify what is the quadrant. So we know that the cosine of u equals 3/5, and cosine is positive in quadrants 1 and 4. But in this particular situation, think about the fact that you have the inverse cosine of 3/5. So if this guy right here is positive, so a positive 3/5, that means I'm getting something back in terms of u in quadrant 1 because of the range of the inverse cosine function. So that tells me right now that u is in quadrant 1. Let me make that q a little bit better there. So once I know that, then I'm just going to go through and say, okay, based on the definitions for my trigonometric functions, the cosine of u is equal to x over r. Remember, x is your adjacent, r is your hypotenuse, and then the sine of u is equal to y over r. So y is the opposite, r is the hypotenuse, and then the tangent of u is equal to y over x. Okay, well right now I have 3 over 5 for this cosine of u, So that tells me that x is 3 and r is 5. So let me write that x is equal to 3 and r is equal to 5. Now, most of you know that y is going to be 4 because this is a 3, 4, 5 right triangle. But let's just go through and figure that out. Let's just pretend we didn't know it. Of course, you could sketch a triangle if you needed to. You can pause the video and do that on your own. I think this problem is easy enough to where we don't have to do that. So we would just use our Pythagorean theorem. We know that x squared plus y squared is equal to r squared. So just coming straight from the Pythagorean theorem, something we did earlier in the course. And basically you would take your 3, so 3 squared, plus, again, let's pretend y is unknown. So let's put y squared is equal to r, which I need to plug in for that. So that's known, so that's 5 squared. So 3 squared is 9, and then 5 squared is 25. And then essentially you would subtract 9 away from each side of the equation, and this would go away. And 25 minus 9 is 16. So at this point, you would use your square root property and say y is equal to plus or minus the square root of 16. Now, we know that we are in quadrant 1. Again, we established that earlier. So in quadrant 1, y values are positive, so I don't need the plus or minus here. I just want the principal square root of 16, and that's going to be 4. And of course, we already knew that because this is a 3, 4, 5 right triangle. But again, if you didn't realize that, then that's how you can go through and figure it out. So at this point, I know that x is 3, y is 4, and r is 5. Now, I don't actually need r in this particular case. I just needed it to figure out what y was. But I'm just going to plug in a 4 for y, and I'm going to plug in a 3 for x. And so the tangent of u, what I was trying to figure out over here, is going to be 4/3. Let me actually erase everything and put this in terms of the original problem. So just coming back up here, the tangent of the inverse cosine of 3/5, that's going to be 4/3. All right, let's take a look at problem 12. So here we have the cotangent of the inverse sine of 3/4. So again, I'm just going to use a little substitution. I'm going to let u be equal to the argument for the cotangent function. So basically it would say this is equal to the inverse sine of this 3/4. And once we do that, we can then say that the sine of u is equal to 3/4. Now, we're going to end up just replacing this, again, with u. So we want to find the cotangent of u. So that equals what? Let me slide down here. I'll come back up in a little while. Remember from earlier in the course that, again, if you know the sine of u is 3/4 and you know the quadrant of u, well, then you can find the cotangent of u. The cotangent of u is going to be x over y. It's the reciprocal of the tangent of u. So what quadrant is my angle u going to lie in? Well, again, this is positive here, so a positive argument for the inverse sine function, that's going to give me an angle in terms of u that's going to be in quadrant 1. So I know that u is in quadrant 1. Now that we've established that, again, we're going back to that basic exercise from the beginning of trigonometry. The sine of u is equal to y over r. So this is your y, that's your opposite. This is your r, that's your hypotenuse. So all you really have to do here is say that x is equal to, I'm just going to put a question mark, y is equal to 3, and r is equal to 4, and just use the Pythagorean theorem. So remember, we have x squared plus y squared is equal to r squared. So x is unknown, so let me write x squared, plus we know y is 3, so 3 squared is equal to r squared. R is known, that's 4, so this is 4 squared. So 3 squared is 9, and 4 squared is 16. And so basically what you would do here is subtract 9 away from each side of the equation. And so this is going to cancel away, and you're going to get that x squared is equal to, if you look at 16 minus 9, that's going to be 7. So by the square root property, you could say that x is equal to plus or minus the square root of 7. Okay, let me actually erase this. When we think about our x values, again, we know that u is in quadrant 1, and so the x values are positive. So I just need the principal square root of 7 there. I don't need the negative, so let's put that in there. And maybe this doesn't fit so well, so let me rewrite this. So x is equal to the principal square root of 7, and then y is equal to 3, and then r is going to be equal to 4. So the cotangent of u is x over y. So what is my x value? Again, that is going to be the square root of 7. And then what is my y value? That's going to be 3. So the cotangent of u is the square root of 7 over 3. Now let me erase all this, and I'll just come back and answer in terms of the original problem. So the cotangent of the inverse sine of 3/4, that's going to be the square root of 7 over 3. All right, for the next problem, we're going to change things up a little bit. For the instructions, we want to write as an algebraic expression in u. All right, let's take a look at problem 13. So here we have the secant of the inverse sine of u over the square root of u squared plus 4. So this problem is actually pretty easy overall. You just need to make a sketch and go back to your SOHCAHTOA. And what I'm going to do first is just make a little substitution like we've made in the previous problems. So I'm going to take the argument for the secant function. So this guy right here, this inverse sine of u over the square root of u squared plus 4. And I'm going to set that equal to a variable. Normally I would use u, but since u is taken, I'm just going to use w. So you see here that I have let w be equal to the inverse sine of u over the square root of u squared plus 4. So then we can say that the sine of w is equal to u over the square root of u squared plus 4. So once I make this little substitution, now I'm just trying to figure out what is the secant of w. Because again, w is this. So let's say this equals what? Now going back to the SOHCAHTOA, remember that if we think about our cosine function, it's going to be the adjacent over the hypotenuse. For the secant function, we take the reciprocal. So this is by definition the hypotenuse over the adjacent, and normally we write that as r over x. Now before we continue, what can we plug in for the inverse sine function? We have this expression here, and we really want to think about, am I going to be able to plug in something that's going to violate the domain of the inverse sine function? And then, is something going to happen where I'm going to violate the domain of the secant function? So you really want to think about that if you're not given any restrictions. So the first thing is, we know that the domain, so the domain for the inverse sine function, so y equals the inverse sine of x, this right here is going to be from -1 to +1, with both being included. So the question would be, is there anything that I can plug in here for u that's going to result in me getting a value that is outside of this domain? Well, to answer that question, I think the fastest way is to look at a graph. You can go to Desmos and just sketch this. What you'd want to do is sketch the graph of y is equal to, let's just say it's x over the square root of x squared plus 4. So you would notice immediately that the domain of this guy right here is going to be all real numbers. So the domain is the set of real numbers. So from -infinity to +infinity. So that tells me if I go back up, I can plug in anything for u. So I can plug in a negative, a positive, 0. And so that is the first part. Now, I need to focus on the result of this, or the range, because the range of this, or the output values here, that's going to become the domain for the inverse sine function. In other words, I plug in something for u, I go through this guy, and I get a result, and then basically I'm taking the inverse sine of that. So looking at the range here, what you're going to see is it's going to work out quite nicely. Looking at the range, it's going to be from -1 to +1, with those guys being excluded. The way you can see it's excluded is that you have a horizontal asymptote at y equals 1 and also y equals -1. So those are those horizontally dashed lines. Let me actually arrow to these and say that this right here is y equals -1, and then this right here is going to be y equals +1. So for the range, let's go ahead and write this is from -1 to +1, with those two values being excluded. So that's why I wrote a parenthesis here and a parenthesis here. Now, let's come back up and let's think about this. So no matter what I plug in for u, again, the domain is all real numbers, the result of this guy right here will be from -1 to +1, with those guys being excluded. So I will never violate the domain of the inverse sine function. Okay, so we've established that, so we're good to go there. Now, let's think about this in terms of the secant function now. I want to go to the unit circle, and I want you to remember, if you have something like the secant of w, this is going to be undefined, so is undefined. Where? Well, basically at pi over 2, 3 pi over 2, 5 pi over 2, 7 pi over 2, so basically pi over 2 plus pi n, where n is any integer. So I'll say is undefined for pi over 2 plus pi n. Now, This would also include something like negative pi over 2. So in other words, if I started here and I rotated clockwise by pi over 2, so this would be an angle of negative pi over 2. Let me get rid of this real quick. So remember, if you take the inverse sine of positive 1, you get pi over 2. And if you take the inverse sine of negative 1, you get negative pi over 2. So if we were able to do that, we would see that our secant function is undefined. But remember, 1 and negative 1 are excluded. So we're not going to be able to get to that. So when we're working in our problem, in terms of that expression, our inverse sine function is going to be working this right here. So basically from negative pi over 2 to pi over 2, with those guys being excluded. So you could really say that w is greater than negative pi over 2 and less than pi over 2. So thinking about that, we're not going to encounter a situation where the secant of w is undefined, because it would need to be pi over 2 or negative pi over 2 for that to happen in this particular case. All right, coming back here, let me just paste this in so this is clear. You could write that down for your notes. Again, like we just talked about, we know the secant of w is not going to be undefined because w is greater than negative pi over 2 and less than pi over 2. Now, looking at this guy, we're going to make a little sketch. If u is positive, so just think about this for a moment. If u is positive, this whole thing's going to be positive. So the inverse sine of something that's positive is going to give me something in quadrant 1. Remember, this is not going to be positive 1. That's excluded, so we're good on that. We already covered that. So basically, if I look at my sketch, I'm just going to cover this part for right now. This is if u is positive. So I know I'm going to get something in quadrant 1 in terms of w. Now let's go back up. The other scenario is, what if u is negative? So if u is negative, well, this whole thing is negative. And again, the inverse sine of something that's negative, you're going to get something in quadrant 4 rotating clockwise. Again, we're not going to have negative 1 here. That's going to be excluded. So you're not going to get a negative pi over 2. So let's go back down and let's look at that. So this is where u is less than 0 or negative. So that's this angle w here rotating clockwise. So now that we've set that up, let's go ahead and say that the secant of w is equal to, again, it's just going to be the hypotenuse. So the hypotenuse over the adjacent. So the hypotenuse is the square root of u squared plus 4. Again, we're getting that from this sine of w equals u over the square root of u squared plus 4. So the hypotenuse is down here. It's opposite over hypotenuse. So that's labeled here as square root of u squared plus 4. So this is your hypotenuse here. It's also labeled here. So this is the square root of u squared plus 4. So remember, the hypotenuse is always positive. In terms of u, it would be positive here and then negative here. So we've already established that. But when we think about the adjacent, because we're either in quadrant 1 or quadrant 4, where x values are positive, well, this is always going to be a positive 2. And the way you work that out mathematically, let me just slide down here a little bit. You can just say that u, again, whether it's positive or negative, it's not going to matter because we're going to square it. So let's go ahead and say that it's u squared plus, you would have, this guy is unknown. Let's just call it x. So x squared, it's going to end up being 2, but you'll see that in a moment. This would be equal to the hypotenuse squared. So let me come down here and say that this would be the square root of u squared plus 4, and this guy would be squared. Okay, well, if I square this, this is going to cancel with this, and I'm going to have the radicand. So I would have u squared plus x squared is equal to, the radicand is u squared plus 4. Well, look at how this is going to work out pretty nicely, because I can subtract u squared away from each side of the equation. This is going to cancel, and this is going to cancel. So this is going to give me x squared is equal to 4. Now I know that I'm either in quadrant 1 or 4, and x values are positive there, so I want the principal square root here. So I would just say x is equal to the principal square root of 4, which is 2. So let me erase all this, and let me come back here. So that's how I get this right here for the adjacent. That's going to be 2. So to answer this problem, finally, after all that work, the hypotenuse is the square root of u squared plus 4. Now we already knew that. And this is over the adjacent, which is what we just solved for. That's going to be 2. So that's going to be the solution for this problem. The secant of w is the square root of u squared plus 4 over 2. Again, where w is greater than negative pi over 2 and less than pi over 2. Let me go ahead and grab this real quick. And I'll just come all the way back up here and answer in terms of the original problem. So let me paste this in right here. And I don't need two equal signs there. So the secant of the inverse sine of u over the square root of u squared plus 4 would give me the square root of u squared plus 4 over 2. All right, for the next few problems, we're going to change the instructions back to say we just want to find the exact value. All right, let's take a look at problem 14. So I'll just tell you in advance, this one's pretty tedious. So you have the cosine of the inverse tangent of 5/12 minus the inverse tangent of 3/4. So the first thing I would do is make 2 different substitutions. I think that's the easiest way to solve this problem. There's other methods you could use. It's really up to you. I'm just going to let something like u be equal to this right here. So this is equal to the inverse tangent of 5/12. And so from that, I can say that the tangent of u is equal to 5/12. And then I'm going to let w be equal to this other guy. So the inverse tangent of 3/4. And then we can say that the tangent of w is equal to 3/4. So first off, I know that if this argument is positive and this argument is positive, then both these angles are going to be in quadrant 1. So I could say that u is in quadrant 1. So I'm just going to do it like this, and then I'll put w that's also in quadrant 1, just as a reminder. So let me actually just grab this real quick, and I'm going to paste this in here. We need a lot of room to work. Let me come back up. So this is u, and this is w. So I'm going to write this as the cosine of u minus w. So let me grab this. So let me paste this in here. Now, most of you have this memorized, some don't. So for your difference identity for cosine, we're going to have the cosine of the first guy times the cosine of the second guy plus the sine of the first guy times the sine of the second guy. So here it's the cosine of the first guy is u times the cosine of the second guy is w, and then plus you have the sine of the first guy, which is u, times the sine of the second guy, which is w. So this is what I need to figure out. I need to get the cosine of u, the cosine of w, the sine of u, and the sine of w. So let's go back up to this right here, and this is where you have to put the work in. So we have that the tangent of u is equal to 5/12, and I know I'm in quadrant 1. For the tangent, it's going to be your opposite over your adjacent, or you could say your y over your x. Okay, so that tells me that x is equal to 12 and y is equal to 5. Now, a lot of you know that r here is 13 because it's a 5, 12, 13 right triangle. But again, you go through the work and you say that this is x squared plus y squared is equal to r squared. Again, r is the length of the hypotenuse. So when we think about this you plug in a 12, you get 12 squared, which is 144. This you plug in a 5, you get 5 squared, which is going to be 25. So that equals your r squared. So 144 plus 25 is 169. So you get r squared. So r squared is equal to 169. So r is equal to plus or minus the square root of 169. But again, your r is always positive. So this is going to be positive 13. Again, we already know that because of the special right triangle. But let's go ahead and say that for the sine of u, it's equal to your opposite over your hypotenuse. So that's going to be y over r, or 5 over 13. And then your cosine of u is going to be equal to your adjacent over your hypotenuse. So x over r, or 12 over 13. Come down here and paste this in. And let me go get the other ones. We'll come back up. So let me erase this. We're going to work in terms of the other one now. So we're thinking about w. So we have the tangent of w is equal to 3/4. So again, this is y, and this right here is x. So this is going to be a 3, 4, 5 right triangle. Again, a lot of you already know that. If you get this on a test, just skip ahead and say, okay, well, r is 5. But for the sake of the tutorial, let's write that x is equal to 4. Let's write that y is equal to 3. And r, let's just put 5 for right now. But again, this was x squared plus y squared equals r squared. If you don't know what it is, x is 4, so 4 squared is 16, plus y is 3, so 3 squared is 9, and this equals r squared. So this becomes 25 over here. 16 plus 9 is 25. And you want the principal square root of 25, which is 5. So r is equal to 5. Let's get rid of this. And now let's write that the sine of w is equal to, again, this is going to be y over r, so 3 over 5, or 3/5. And then the cosine of w is going to be x over r, so that's going to be 4/5. Okay, let's come down here and paste this in and put a little border there. And hopefully this all fits on the screen. So the cosine of u is 12 over 13. So let me put that this is equal to 12 over 13. And then times the cosine of w, that's going to be 4/5. So 4/5. And then plus the sine of u is 5/13. And then times the sine of w, that's going to be 3/5. Now you could cancel this 5 with this 5, but notice that you're going to have a common denominator if you leave it alone. So I'm not going to touch that. So I'm just going to go through and say 12 times 4 is 48. And then plus 5 times 3 is 15 over the common denominator of 13 times 5, which is 65. So this right here, 48 plus 15, that's going to be 63. So this is 63 over 65. So coming back up, I'm going to say this equals 63 over 65. All right, let's take a look at problem 15 now. So we have the tangent of, we have 2 times the inverse sine of 2/5. So let me slide down here a little bit. I'm just going to make a little substitution. So let u be equal to this part right here. So we're going to say the inverse sine. So the inverse sine of 2/5. And again, that tells me that I'm going to have the sine of u is equal to 2/5. And u is going to be in quadrant 1 because this guy is positive. Again, if you have a positive argument for your inverse sine function, you're getting something back in quadrant 1. So let me just write here that u is in quadrant 1. So what I'm going to do is replace this and say it's tangent of 2u that I'm trying to figure out. So the tangent of 2u. So let me grab this and come down here and paste this in. And let me put this in there that got erased. So at this point, if we want to find the tangent of 2u, remember we have a little formula for that. Let me actually grab this and come up here. I have the formula already written out. So the tangent of 2 theta equals 2 tangent of theta over 1 minus tangent squared theta. Okay, so the tangent of 2u is equal to 2 tangent of u over 1 minus tangent squared u. So the first thing is you need to find the tangent of u. How do we do that? Well, at this point, we have the sine of u. Again, we know it's in quadrant 1. So this right here is going to be your y value, or the opposite. And this right here is going to be your r value, or the hypotenuse. So you need to find x, or the adjacent. So if I know that x squared plus y squared is equal to r squared, I can just plug in. So plug in a 2 for y, and then plug in a 5 for r. And then basically you're going to get x squared plus 2 squared is 4 is equal to 5 squared is 25. Subtract 4 away from each side. So x squared would be equal to 21. So x squared is equal to 21. Again, we're in quadrant 1. So x is equal to the principal square root of 21. Again, you don't need the plus or minus because you know you're in quadrant 1. X values are positive. Okay, so that tells me that the tangent of u is equal to, again, it's y over x. So this is 2 over the square root of 21. If you rationalize the denominator, you multiply by the square root of 21 over the square root of 21. This gives me 2 times the square root of 21 over 21. Okay, let me get rid of this. And I'll just write this in here more cleanly. So 2 times the square root of 21 over 21. Okay, let me get rid of this. Now, all you have to do is take this right here and plug in everywhere you see tangent of u, and basically you're home free. So I'm going to replace this tangent of u with 2 times square root of 21 over 21. And then this is tangent squared u. So what I want to do is plug in for the tangent of u. So 2 times square root of 21 over 21, and this would be squared. Okay, let's say equals. We're going to come down here. I'm going to do this in a slightly different way. So this is just multiplication. So 2 times 2 is 4. So I'm just going to write this as 4 times the square root of 21 over 21, and this is over. For this one, let me first write 1 minus. This is 2 times the square root of 21 over 21. So this would be 2 squared times the square root of 21 being squared over 21 squared. Now I'm doing that for a specific reason, and you'll see that it's going to make it easier. We can do this without a calculator. So first off, we know that this would just be 21. So I'm just going to erase that and say that this is 21. Now this would be 4, so you can write that in, so 4 times 21 like that. Now, before I do anything else, notice that you have 21 here and 21 squared here. And to make that crystal clear, you can write this as 21 times 21. So of course, this would cancel with this. So I'm just going to erase it, make it a little bit quicker for us. So this is 4 over 21 here. So I'm going to write this as 21 over 21. I can go through and say that this is equal to 4 times the square root of 21 over 21, and then over 21 minus 4 is 17, and then over the common denominator of 21. So this equals, you're going to have 4 times the square root of 21 over 21 times the reciprocal of this. So this is 21 over 17. So this right here would cancel. And what I'm left with is, let me write this down here. So 4 times the square root of 21 over 17. So let me copy this real quick, and we'll come back up here and just give our answer in terms of the original problem. Let me paste this in here. That color really doesn't show up well, so let me change it to green. So our answer here is 4 times square root of 21 over 17.